Hi, I'm Shri, and this is Machine Learning Under the Hood, where I go over machine learning concepts and build them from the ground up. In this video, I'll be going over regularization, specifically Lasso and Ridge regularization, and at the end, elastic net as well. So regularization improves stability over your machine learning model by adding onto your cost function an extra term that penalizes large gradients. What exactly stability is, I'll go over the next slide, but for now I'll go over the formulas for Lasso and Ridge. So here we have lambda times the L1 norm of theta, where theta is a vector containing all our parameters, as you can see in the purple box here. And Ridge, instead of the L1 norm, we use the L2 norm, and then we square it. And the formula for that can be seen here. And an example, so our cost function in the case of the sum of the squared errors for j of theta, as you can see in the blue box here, we add on lambda times the L1 norm or lambda times the L2 norm squared, depending on Lasso or Ridge. So this extra term we add on to the cost function then means we get penalized, as I mentioned earlier, for larger weights. So the difference between the two is how the penalty term actually looks. So these two graphs here represent how the weights are penalized differently. For y equals lambda x, absolute value of x, the gradient is constantly plus or minus lambda depending on which side you are, but the absolute value of the gradient does not change. So the penalty does not change for the size of our gradient, or for the size of our parameter, which will have some knock-on effects, which I'll go over later in this video. Unlike this, y equals lambda x squared, which corresponds to Ridge. As you can see, we're squaring the parameters here. This is smooth everywhere, and the amount you penalize decreases as you get closer to the origin. And in fact, because the gradient is 2 times lambda times x, so it's a linear function of x, the penalty is proportional to the size of the parameter. And it's differentiable everywhere, unlike lambda times the absolute value of x, which can't be differentiated at the origin. So stability, I briefly mentioned it earlier, but if we have something that is unstable, you see the gradients are massive here in this bottom left graph. So you see the prediction spikes up really high and then goes down really low, and this oscillation everywhere isn't indicative of how real life variables work out. This isn't what the relationship between two pieces of information typically look like. And so what's likely is this has been overfit. It's deviating because of noise in the graph, and it's not capturing the essence or the genuine predictive value of the features for our target. What this means is it's probably not very repeatable. If you give it a different data set, this probably wouldn't match it very well. So one way of nullifying this is regularization. So this is lambda equals 0, where there's no regularization. And if you go to lambda equals 0.05, this isn't exactly what it would look like, but it gives you an idea. It sort of removes some of the kinks. It penalizes large gradients, so the gradient generally is smaller everywhere, and it just looks more stable, and it's more repeatable. And if we increase lambda to 0.5, again, some of the kinks are gone. The gradients at every point will be smaller because we're penalizing larger gradients with our cost function. And just to make a point, lambda equals infinity gives you a completely horizontal line. So as you increase lambda, you're actually stretching the graph horizontally like this and making it more and more like a horizontal line. Obviously, you'd never have a huge lambda where you just get a horizontal line, but just making the point of what this is doing, it's ironing out massive gradients and it's converging to a horizontal line as you increase lambda. And this 0.05, 0.5, this is typical range for lambda that you would actually use in practice. Generally speaking, lambda is chosen through trial and error. You don't mathematically come up with some perfect lambda value. Just like with everything in machine learning, you trial and error and heuristically look at what works best. So some properties. So Lasso implies a Laplacian prior on our parameters, whereas ridge implies a Gaussian prior on our parameters. So this is something I'll actually go over in the next video in much more detail, because this is part of a much bigger interlinked network among machine learning. But for this video, a Laplacian prior is essentially saying if we take any of our parameters, say θ1, before we've even looked at any data, we are assuming that θ1 follows a Laplacian distribution. I've written the distribution below in pink. This is just an exponential decay, with a b being some constant that we can scale the decay by, and mu being our mean. This is just an exponential decay, and we're imposing this distribution on θ1 before looking at anything. We're just assuming this is the distribution. And when you optimize for a cost function that uses Lasso, so that lambda times the L1 norm of theta, when you include that, immediately you are assuming a Laplacian distribution, which sounds quite counterintuitive. And I'll be proving the maths behind this, as I mentioned, in the next video, when I look at the more broad result that this is a specific case of. Likewise with ridge, we're assuming a Gaussian distribution for our parameters. I said θ1 as an example, but this is true for every individual parameter. So when you have lambda times the L2 norm of theta, and you minimize with that extra term, immediately you're imposing this Gaussian prior on each parameter. Again, quite counterintuitive. So on top of this, back to Lasso. Lasso increases the sparsity of theta, which basically means you will have more zero terms when you optimize for this cost function. This is something I'll be proving in another slide. But this just makes the maths quite simple. So a lot of terms are canceling out. When you're multiplying it by anything, it's computationally quick. So this simplification through sparsity is quite useful with Lasso, though it does have its limitations as well, which I'll go over. So in the case of ridge, like I mentioned before, because squaring, so our theta I squared times lambda, this is differentiable everywhere, unlike when we take the absolute value, which is quite useful, because when you use, say, gradient descent, this explicitly requires the gradient to compute each step. So it being differentiable everywhere means you can easily calculate every single step. Whereas for Lasso, the absolute value is not differentiable when this parameter equals 0, as I mentioned before. So when you're trying to use gradient descent, that causes a problem. I won't be going over the workaround for this, but just know that this does cause an issue, or not an issue, but a complication when it's not differentiable at 0. And as we mentioned, it more commonly falls at 0. It's not like this is a rare edge case. This is an issue you will have to actually create a workaround for due to the sparsity. So again, with Lasso will pick one variable of a set of correlated variables. So say θ1, θ2, and θ3 were all correlated. That means there is redundant information between these three variables. The correlation means that there's an overlap in predictive information. And the way Lasso deals with this, it sees that there's this redundant information, and it only picks one variable. So it might choose θ1, for example, incorporate that into our prediction, and then really heavily penalize θ2 and θ3 and weight them very smallly. So this stops the overlap of correlation. We don't count it 3 times, but a disadvantage of this is we then don't get the genuinely predictive information of θ2 and θ3 because they've been weighted so lowly, and we only get the signal for θ1. Ridge, on the other hand, is able to distribute weights over correlated features more evenly and more fairly. So this is the complete opposite. So it's not all in on one variable, which means you can keep the predictive information of all your correlated variables while not overcompensating or multiply counting multiple times this correlated part of all these 3 variables. So this allows you to keep the predictive information of your 3 variables, but also scaling down the weights of the 3 so that the overlapping information that is contained within these three variables isn't triply counted. So going to Lasso, there's a uniform penalty among our parameters, unlike Ridge, which penalizes smaller parameters less. This is for the reason I mentioned earlier, where the gradient is smaller as you get closer to the origin here. It gets smaller and smaller, and it's bigger as you're further away. Whereas here, it's always just lambda. So that's just a trait of Lasso and Ridge. And finally, there's an invariance over rotation for theta with Ridge. The reason for that is because the L2 norm is actually just the distance from the origin of a vector. So this L2 norm squared is just the squared distance from the origin of theta, which means if you change the parameters in a way that the distance is preserved, that won't actually change this error term, or this extra term, should I say, this normalization term. This is literally just dependent on the distance. So what that means is if you rotate around the origin, preserving the distance, this term does not change. So this gives us symmetry around the origin. So that's just another feature of Ridge. So now that sparsity point that I made earlier, I'll be explaining that in a bit more detail. So we want to minimize j of theta, and j of theta looks like this. So in the case of sum of the squared errors, you have this first term here, and then the second term here. But at theta I equals 0, if this term grows slower than this term in every direction, that inherently implies that we're at a minimum, because otherwise, if it decreased in a certain direction, the cost function has gotten smaller and we weren't at the minimum, because it's getting smaller when you move away from your point. A feature of a minimum is no matter how you move on the curve, you're always going to increase your value. But the thing is, because of this non-differentiable point, this corner, it means you have a big range of gradients where this is true. I'll show you what I mean now. So if we look at this graph here, there's a lot of different gradients where you see here on both sides of this black dot I've just drawn here, we're below the curve on the left and the right. And there's lots of gradients where this is true. You can draw lots and lots of gradients. Whereas here, if you do that, if you rotate it a bit, like here, that's not a good example. Usually when you have a tangent, sorry, these are terrible tangent lines, you touch it at one point, and if you rotate it, you'll intersect the curve, and now you're above the curve, and you've actually made it bigger than the curve. So in one direction, it's less than the curve. You see, you have to drop down to hit the black line, the black tangent line. But here, you've had to go up when you rotate it. A tangent line has a property that on both sides of the point of tangency, you're always below your curve, which means it's always less than it. And usually you can't rotate your tangent line and this still be true, but here you can draw all kinds of tangent lines and still be below the curve everywhere. And in fact, if your gradient is between alpha, which is this line here, and minus alpha, you will still be below this curve at every point. What this means is there's this big range of gradients that your sum of the squared error terms can have, where you are still below the curve at every point because of this rotation point that I've just made. And so I've written it here. If your sum of the squared error terms, if the gradient, if its absolute value is less than lambda, or another way of writing it is like this, then theta j equals 0 gives you the minimum, because on both sides, if you walk left or right, you're still below the original function line. And this is because you're still decreasing regardless of whether you walk left or right, even when you rotate the tangent line. And this big bucket of gradients means it's really susceptible to getting theta j equals 0 as being the minimum. So I've got a geometric demonstration of this here. So if this is a bird's eye view of θ1 and θ2 being our two parameters, and then a third axis being the height for the cost function. So this is, you can't really get the depth here, but this is meant to be a 3D graph from a bird's eye view. And j of theta here, this is an outline of j of theta being tangent to this diamond and this circle. So these diamonds represent a constant value of the L1 norm, and these circles represent a constant value of the L2 norm. So here, the L1 norm equaling 2, 1, and 0.5 respectively for these three different colors. Likewise, 4, 1, and 0.25 for the square of the L2 norm are demonstrated by these three colors here. So j of theta could be anything really, and we can just scale this diamond so it's tangent. So we could have another diamond here if this is another j of theta, and this would be like 1.25 or something for this red diamond that I've not fully drawn here, but then it would look like that. So the point I'm making is you can scale this diamond to be whatever you need so that it's tangent to your cost function, and that would be your minimum when you also add this normalization term of the L1 norm times lambda. So keeping that in mind, we see that this diamond shape, this point, makes things susceptible to hitting specifically at this corner. Unlike the circle here with the L2 norm, where there's no edge, and so it's way less susceptible to hitting zero. Because if you slightly change it, this edge just pokes out and hits it, and it just makes it way harder to dodge. Whereas this smooth circle, if you slightly adjust the tangent, it just means it'll slightly adjust where the point of tangency is. And this is essentially the same argument of that bucket term of the gradient being between lambda and minus lambda. It catches this edge if it's not between those values. It can still hit somewhere else, but you need the point of tangency. You need the gradient to be not between minus lambda and lambda. Otherwise, it'll catch this edge. And so I've written out the formulas here as well so you sort of see how it comes back to Lasso and Ridge, because Lasso and Ridge is about penalizing these absolute value terms or these square terms. So hopefully that made sense. This j of theta, this is an outline of a surface. J of theta is a surface here, but I've just drawn a line to represent the outline where it's hitting these norms and as a tangent. And finally, we have elastic net, which is a combination of Lasso and Ridge. So on top of our lambda term to change how much we're penalizing the weights, we have a second parameter, alpha, and alpha changes how much Lasso and how much Ridge we want to include. So it changes the proportions of the two. When alpha equals 0, this L1 norm term disappears, and this L2 norm term is just 1 minus 0, so it's just the entire term. Conversely, when alpha equals 1, you get just the L1 norm term, and 1 minus 1 goes to 0. This L2 norm term disappears. When alpha equals 1/2, you get 1/2 here, 1/2 for L1, and 1 minus a half. That just becomes a half as well for the L2 norm, and you have equal proportions of the two, and you can have anything in between as well. The advantage of this, you still keep some of the sparsity of L1, whereas you also keep some of that weight spread term that I mentioned before over correlated variables from L2. So you're not all in on one variable when you have multiple correlated variables. So this is sort of a compromise for the best of both worlds. If I go back to the geometric demonstration, what elastic net would look like is something in between with this red line I'm drawing here, where it's not quite a circle, but it's not quite a diamond either. And it still has, at the edge, it'll have this corner here. So that argument of susceptibility to, catching tangent lines and being way more likely to hit 0 is still true. But at the same time, it still has that ability to distribute weights. So with this, it still has this little corner here. Even though it's not a complete diamond, it still has a point of non-differentiability here. I'm not represented very well, but that means tangents will still catch on it even though it's smoothed out a bit. So you still get that sparsity property. So if that's what you want, that's a pro of elastic net. So that's everything on regularization. In the next video, as I hinted at earlier, I'll be going over a very interesting result in machine learning that explains why we use some of the squared errors, why we use these particular norms for normalization, and in general, just a family of cost functions and a family of regularization functions that we use and why we use them, because it's not arbitrary. So stay tuned for that, and I'll see you in the next video.